Okay, so this video is going to be over how we prove continuity and what it means to be a continuous function, how we can use calculus to prove those things. So your target for this one is students will determine if a function is continuous at a given value by applying the definition of continuity to see how a limit is related to the continuity of a function. Okay, so let's look at what it means to be continuous. So we talk about continuity at a point, and we say that the function of f is continuous at x equals c. Anytime we use a c value, what we're talking about is a specific x value. That is very messy. Let me rewrite that. We say a specific x value. We often use a c to represent some type of value. So it's continuous at x equals c if and only if the limit as x approaches a of the function is also equal to f of a. So what that means is our function exists and our value exists, and the fact that they're equal. So there's really three requirements or three conditions for us to say that f is going to be continuous at a. The first one is that f of a actually exists. So let's say we have a graph. Let's say that this is A. So we know we have a definite point at f of A. Second thing, the limit as x approaches A of f of x exists. That means we do not have a jump, which of course is a discontinuity. There's no oscillation, and there is no vertical asymptote. So the limit as we approach that value for a particular function, of course, exists. And then the most important part is that the function is equal to this limit value. Okay. So all three parts have to be true in order for us to say that something is truly continuous. If one of them fails, then the function is not continuous based on definition of continuity. Okay, so let's look at a problem. We want to justify that the following is continuous at x equals 3 by using the three conditions of continuity. Because this is a piecewise are known for having those jumps, those possible discontinuities. So the first thing I want to do is look at the limit, especially at the value at which our function changes. So 3 in this case. Because this is a piecewise, I automatically know that I have to evaluate the limit. That is terrible. Let me erase that really quickly. That the limit as x approaches 3 from the positive side needs to be evaluated, and the limit as x approaches 3 from the negative side. So we're going to start with that idea of the limit. Remember, I have to choose which part of my function represents each. So it's 3 from the positive side, so that means we're talking about values greater than 3. So according to our inequalities, that's our second equation. So I'm going to use that one to evaluate. And of course, the other one should be here. So I'm just going to plug in a 3. So we have 15, or 5 times 3 minus 1, which is equal to 14. And on this one, 3 squared plus 5, which is equal to 14. And what this means is that the limit as x approaches 3 from both directions of this function is equal to 14. So our limit does exist. Okay, we've just used our definition of a left-sided and a right-sided limit to prove that. I also want to look at the value of f of 3. So because this is piecewise and we're looking at the function value, we're looking for the equalness, which is our top equation. So we've already plugged this in, but I'm just going to do it for emphasis. And we get 14. Because these two values are the same, we can say f of x is, in fact, continuous at x is equal to 3. And here's my justification. Since the limit as x approaches 3 of our function is equal to f of 3, the true definition of what it means to be continuous. Okay, so let's look at the next slide. So when we talk about a function being continuous on an open interval, okay, that means we're not really looking at the endpoints, but we're looking at all the points in between. It's only continuous on the open interval if it is continuous at each point within the interval. Again, we're not talking about the endpoints. We say that the function is continuous over the real number line, so negative infinity to positive infinity is everywhere continuous. So a lot of the functions you've dealt with, like our polynomial functions, are going to be continuous everywhere because they exist for every value of x. There's no type of discontinuity on them. Okay. When it comes to discontinuities, there's 3 types of discontinuities. You already learned these in Algebra 2. We've talked about these in class. So we have the removable. Okay. Here the limit exists, but the function does not. So limit exists, but f of a does not. So it already fails on the first one, which means that it's not continuous by the definition of continuity. So if that were, of course, a. The second one is an infinite discontinuity or an vertical asymptote. Okay. Here both f of a does not exist, and the limit does not exist. Okay. So 1 and 2 of the definition of continuity are not met. The last one is a jump discontinuity. Okay. And of course, the f of a exists, but the limit as x approaches a of this function does not exist. So it meets criteria 1, but does not meet criteria 2. Therefore, we call it a discontinuity. When it comes to the classification of a discontinuity, there's only technically 2 classifications. Okay, so the first classification is, of course, the removable. Because of the fact that we can actually work around it, the limit still exists there. We just have to remove it from our equation to find it. And then both of these fall into the second category, which we call these the non-removable. I think that is not how you spell non-removable. There we go. Okay. And the reason for that is the fact that there's nothing we can do algebraically to work around it. On both of these, the limit is going to fail to exist. Whereas on the first one, we can still evaluate the limit about the approach. Okay, so when we talk about non-removable, we're talking about our vertical asymptotes and our jump discontinuities. When we talk about removable, that is our removable discontinuity. So let's look at another example. So I want to look at all 3 of these functions and talk about the continuity. So if we think about the function of 1 over x, I know that there is a non-removable discontinuity at x is equal to 0, because that's what's going to make it undefined. There's no type of factoring or simplification that is going to remove that x in my denominator. The second one is a removable. Discontinuity. And it's going to be at x is equal to 1. That's what's going to cause my denominator to become 0. But if I factor my numerator, the fact that I can remove it from my equation and work around it is what classifies it as a removable. And the last one, our sine function. As we saw on Wednesday, our sine function, in fact, is continuous everywhere. There are no discontinuities at all. If I wanted to, I could draw the entire sine function forever in both directions without the idea of lifting up my pencil to complete the graph. Okay, so sine of x is continuous everywhere. A lot of times our discontinuities are going to show up in our rationals functions like a and b, or piecewise functions like on our previous examples. Okay, let's look at another piecewise function. So I want to define f of negative 1. I want to know what this value must be in order to actually make our function continuous everywhere. Okay, let me erase that really quickly. Okay, so I'm looking for what value this has to be in order to make this continuous. Because we are talking about continuity, I can use my definition of continuity to actually figure this out. So I always start by defining continuity by looking at my limits. Now, if we think about it, this one's a little bit different because of the fact that we don't have an inequality, we have an equal sign and a not equal sign. So this is the value of my function. Okay, that's my f of negative 1. That's what I'm trying to figure out. Okay, so I'm trying to figure out what f of negative 1 must be. The other one, this one right here, this is another way to write this is we can say x is greater than negative 1 and x is less than negative 1. So both of my inequalities fall on the same part of my equation. Therefore, I don't need my left-sided limit and my right-sided limit. My left-sided limit and my right-sided limit are the exact same equation. So I can just use one of my limits, my one-sided limit, not my one-sided limit, but my both-sided limit. That made no sense, but I just need to do one limit. So first thing, of course, is to look at my equation. So I know my denominator is going to wind up being 0. I'm going to double check to see if my numerator is going to be 0, because then I can use one of my new methods. So if I plug a negative 1 in here, I'm going to get 1 minus 5 plus 4. And that does, in fact, equal 0. So I have a 0 over 0 situation. So my go-to method, of course, is, in fact, factoring. So that's exactly what I'm going to do. If I factor the top, I get x plus 1, x plus 4 over x plus 1. That's going to cancel out, which leaves me with the limit as x approaches negative 1 of x plus 4, which gives me negative 1 plus 4, which leads to 3. So my limit exists. My function, we're just trying to define to make it exist. But my third part of the definition is that my limit of this function must equal f of negative 1. If we think back to that third three-part definition, my function, which is the top line, my limit, the second line, and the fact that both of those are equal. Well, I know the value of my limit. The value of my limit is equal to 3. So this must be equal to f of -1, which means my question mark from above must equal 3. So using that definition of continuity, ooh, don't box that. Ignore that I did that. Didn't happen. So definitely using that definition of continuity can even help me answer a question like this. Let's look at another one. So it says to find the constant a so that the function is continuous on the entire real line. So we're going to make it continuous everywhere. Again, we're talking about continuity, so I'm going to use my 3-part definition, always going back to that definition. On this one, I'm definitely going to have to use a two-sided limit, or a one-sided limit, because of the fact that I'm dealing with inequalities. So I'm going to look at my limit as x approaches 2 from the positive side, and the limit as x approaches 2 from the negative side. Okay. So from the positive side, I'm looking for greater, so ax squared. 2 from the negative side, I'm looking for less than, so x cubed. It's really important that we establish which equations we're using for each of our limits. We're going to be very specific with that. So limits are all about the plugin, so that's what we're going to do. So this gets us to 4a. We don't know what a is, but my limit process leads me to that 4a, and I'm going to trust that right now. Here we go, 2 to the third equals a. In order for my limit to exist, these two values must be equal. So what am I going to do? I'm going to set them equal to each other. And of course, solve for a, so a is equal to 2. If we put a 2 in here, that's going to give us 8. Sorry, if we put a 2 in here, that's going to give us 8 when we plug in the other 2. And of course, we're going to plug in 8 to there, and both of the sides of our function are equal to each other. So our function is equal to our limit if, in fact, our a value is 2. Okay. This last one, what I'm going to do is we're going to start class on Friday